Today we will be introducing path planning for automatic parking based on distributional soft actor critic. We tackle the issue of automatic parking using deep neural networks and reinforced learning. We are able to construct effective pathings for vehicles in a variety of scenarios, such as parallel parking and reverse parking. With development of technology, self-driving cars have also become smarter and capable of performing more difficult tasks. Automatic parking, as an integral part of self-driving cars, often requires the driver to first position the vehicle in designated areas. Our project aims to remove restrictions, allowing the car to perform automatic parking regardless of location, orientation, or angle of approach. Our environment is set in a simulated parking lot, where the initial location and angle of the car is random, and the destination is the space with the blue rectangle. The red line shows the direction the car is pointed, and is used to indicate whether the vehicle is going forwards or in reverse. Here are the specific details of our simulated parking lot. Most automatic parking methods will first calculate the trajectory of the vehicle, then design a controller that will steer the car towards its desired destination. However, such an approach tends to be time-consuming and requires large amounts of manual tuning. To address this problem, we employ the soft actor method in reinforced learning, which uses computer-simulated parking to generate training data, and outputs controllers that will steer the vehicle. The advantages of our methods include reducing manual labor and time consumption by replacing artificial tuning. In addition, when creating the controllers, human engineers are often limited by the mathematical model they choose, and the result they achieve may not be the optimal solution. By training them large amounts of data, we can achieve parking trajectories more optimal than that produced by human engineers. Our mathematical model is based on the Markov decision process. We use OpenAI Gym to create an environment for automatic parking, and define the state of the vehicle as a matrix containing the x, y coordinates, horizontal and vertical velocities, and turning angle of the car. The is the acceleration and turning angle of the next step, and will be rewarded by approaching the destination, and penalized when making contact with out-of-bounds areas. Here is the car model we used in our project. The width of the car is 2 meters, and the length is 5 meters. In our simulation, we can measure the 2D location, velocity, acceleration, and turning angle of the vehicle, which will be given to the agent to evaluate the car's next step. Controller design using reinforced learning can be split into either discrete or continuous methods. Discrete methods include DQN, Deep Q Network, DDQN, Double DQN, while continuous methods include DDPG, TD3 and Soft Actor Critic. Our project employed an off-policy approach, meaning that past simulation results can be used to update policies, while on-policy approaches such as TRPO require new simulations. Additionally, compared to other off-policy methods such as DDPG and TD3, Soft Actor Critic displays less sensitivity to changes in hyperparameters, making it easier and less time-consuming to train. Traditionally, SAC updates its policies based on the expectation of Q values. Recent studies have shown that if SAC instead updates its policies based on the distribution of Q values, better results can be achieved. Our project implements the change to obtain better accuracy and results than previous works, and have achieved over 95% accuracy in reverse, parallel and mechanized parking. So far, we have achieved accuracies of 97.3% in reverse parking, 95.7% in parallel parking, and 96.5% in mechanized parking, respectively. Due to mechanized parking spaces being narrower and thus more difficult to train, we opted to limit the initial angle of the car to less than 36 degrees. Moving on, we will attempt to remove such restrictions and further improve upon the performance of our model in various scenarios.